Greetings, Earth enthusiasts. If you ever wondered about the incredible perspectives our planet has to offer from high above, you're in the right place. I am Dr. Clive Coetzee, and I'm thrilled to be your guide on this captivating journey into the world of remote sensing. Welcome. And please remember to like, subscribe to, and share this video. Thank you.
As I mentioned in my previous video tutorial, we're taking a bit of a detour from our Earth Engine tutorials or work or exploration or journey, whatever you want to call it. And we're doing a little bit of a short series on use of GeoDA. And the reason I'm doing that is just to show that we don't have to just work within Earth Engine per se. There is some other programs or software that we can use that's also very beneficial to our work on remote sensing. But as I keep on always saying, it all starts in Earth Engine, whether it is generating the images or the data or whatever, it all starts with Earth Engine. And then from Earth Engine, it flows down to, as I said, I've got, my 4 or 5 favorites that I work with, and one of them is GeoDA. So we've done now, 1, 2, 3 video tutorials on GeoDA, and as I said, I use it quite a lot. It has fulfill a specific function, and for what it's built for, as what they say, that it says what it says on the tin. It does what it says on the tin. So from that perspective, it's very useful. So in the previous video tutorial, we specifically looked at the weights manager and generating spatial weights matrices. And I said that is one of the major plus points of GeoDA, and one that I personally use a lot, and that is generating weight matrices. And that weight matrix you can import in, for example, into RStudio, and use it in your spatial econometrics or economics. So we spent a bit of time on the spatial weights matrix, and we generated a lot of spatial weights, different spatial weights. Let me just quickly minimize here and then open it up there. So let's continue with that. So we've generated the spatial weight matrices. We showed the differences between, we first showed all the different options that are available in the manager, in the weights manager. And then we actually generated those spatial weights matrices and we compared them. But it's really when we apply them, that's when the real differences materializes or become visible, is when you apply it. And one of those is when we work in the space tab here, the space functions that's available in GeoDA. And you'll see they basically grouped into 1, 2, 3, 4, 5, 6, 7, 8 sort of groupings. The first group is the Univariate Moran, the Bivariate Moran, the differential Moran, and then we get to the local one. So you'll see, this group, the first group and the second group are very similar, except the one is sort of the local and the other one is the global. And we'll get to the differences later. There's some local G statistics, but we're going to play around with that and see what the outcome, the results that these functions yield, where we can apply them or where it's useful, and also how they differ from one another, etc., etc. So, as I said, that is most probably within GeoDA the function that I use the most. The regression, this regression port, that is what okay, let me not go there. Let's just continue with space before I get in front of me. Okay, so to do this space, to do these functions, the spatial functions, the correlation functions, because that's basically what they are, they're correlation functions. We need that spatial weights matrix. Okay, so first of all, every time you open GeoDA, you'll have to reactivate or reload your spatial weights matrices. So we're going to go to our weights manager and you'll see it's empty. Now we have created them, so we're not going to create them now. We're just simply going to load them, and you'll see these are all the ones that we have generated. So you can't multiple pick them, you have to do them individually. So let's do that one. Reload. the second one. So that's order 1 and order 2 queen. And then we're gonna go, sorry, not great. Then we're gonna go load. Let's do the rook 1 and rook 2. Although we showed that there's no difference between rook and q and queen because we're using points predominantly. And that is our band option. That is our k nearest, where we forced it 4, and that is a uniform. Okay, so that's all the weight matrices that we now have loaded. Okay, so once we've loaded all our weight matrix, I'm not going to go to all the histograms and stuff. That's just part what we've done in our previous video tutorial. Now let's start with the functions, the correlation functions, and that's what the Moran I statistics is all about. It's basically a spatial correlation statistic. Okay, it's a spatial correlation statistic. It indicates how spatially correlated your region of interest is, meaning what is the correlation between a location and its neighboring locations. And that definition or that structure between itself and its neighboring locations is where the spatial matrix comes in. It presents that structural relationship between the locations. And so inter to the Moran I statistic is the spatial weights matrices. You cannot do these functions without the spatial weights matrix, as it does define or conceptualize the relationship between the neighbors. And that is then calculated to say whether they are correlated or not correlated, whether they influence or don't influence, or they positive influence or the negative influence. So the Moran's, the I statistics is in the same parameters or same values as a normal Pearson or any of these normal time series correlations between -1 and 1. Okay, so it's got the same interpretation, but just from a spatial point of view. 1 being they are very strong, spatially correlated. Positive, strongly. 0 meaning there's no correlation. Negative or inverse, inverse 1 or -1, meaning there's a very strong, but it's inverse related. So the interpretation of these statistics are similar to the normal correlation in time series statistics. So this doesn't focus on time. It focuses on space. But it's at the same application, same interpretation. Okay, and as I said, we need to generate the weights matrices before the time. Now, just before I go further, let me just go to the website where you can find the cheat sheet for GeoDA, which is very interesting because it gives you a nice little. It basically recreate the tabs that you will find within GeoDA. So these tabs here that you'll find in GeoDA. So we're looking at space, and so we're going to go to space. There they said spatial autocorrelation. There they said, and so if you click on any of these ones, it will take you through the ins and outs of each of these functions or options, which is very useful. Okay, so sit with this. And then you'll be able to understand, interpret all of these functions. Yeah, let's quickly start then. So enough bubbling. So let's calculate the univariate Moran I statistic. So first of all, it's going to ask you a variable. So let's go to our ndvi variable, one that we used as our dependent variable in most of our analysis so far. So let's do that. Okay, so we're gonna click OK. And our second point is we must choose our weights matrix. Okay, so that's important, is to choose our weight matrix. And what we're gonna do is we're just gonna quickly run through them. We're just gonna quickly run through them to see whether they are similar or they are different, or this or that or this or that. Okay, so let's quickly have a look and see. Okay, so ndvi, we're gonna go order 1, queen weight order 1, and there we go. So let's make it a little bit bigger, and there's our spatial weights our Moran I statistic for each of these locations. So you'll see there on top, it tells you the Moran I is 0.829. So that means our locations are spatially correlated, highly spatially positively correlated. And we can, as similar to all of these, we can press on the individual locations and show you that location is not spatially very correlated. Let's quickly choose a location that is very, let's see that one there. And that one there is spatially very correlated. And you can see the difference. That one was, see this one here is you'll see it's next to one another. There's a couple of locations that's very close to one another. And if we look at that one, yeah, it's not that close. It's sort of, yeah, it's landing there. So it's spatially not correlated with all these one. Maybe that one there. This one here, how that one looks like. Come on. That one is this one here. So that one there. So also there's some gaps around it. That's the values. So it tested by its lag. You'll see that's the lag ndvi and the actual ndvi's. Come on. That's the lagged ndvi on the y-axis and the ndvi on the x-axis, and it generates the correlation between the two. And the value is 0.8. If I right click on this correlation, not on any of the Moran I statistic, if I click on any place, right click on this one, you'll see you can go to, okay, there's the selection shape, you can do view. Okay, so have a look at that. But that's randomization. Okay, so here it calculates or it generates a p statistic, probability statistic for that 0.829. So whether we want to find out whether that is statistically significant, is this correlation statistic, this Moran I statistic 0.82, is that statistically significant or not? And to do that, we use the randomization function. And I'm going to go up to this amount of randomization, and we press OK. And it will give you here at the bottom, it will tell you the Z value. There's a P value there. See, 0.001 at 999 permutations. So this does suggest that, and we can run it again, we can run it again. It doesn't matter, it stays the same. So that suggests that this value is indeed statistically significant. Okay, so just go back. How do we determine the statistical significance of this value? Any place on this graph, you just right click, okay, on your mouse, you right click, you go to randomization, and you select the randomization. Let's go 99, still 0.01, it's smaller than the 5%, it's statistically significant. Okay, you see there's the 0.829, mean value, standard deviation, Z value, that gives you your P value. Okay, so that is, remember the value is 0.829. So that's basically calculating the univariate Moran I statistics. And as I said, randomization, statistically significant. Let's quickly do the bivariate Moran I statistic. Let's click that. Now you see it's got two variables here. So let's go ndvi and let's select rain. Okay, so and we're going to keep it. Okay, before we go any further, let's quickly go back to space. Univariate, let's keep it. I'm not going to use the queen 1, I'm going to use the queen 2 and see what that value is. Because remember, the queen 2 has a much wider neighborhood reach. So it's not just my neighbors, it's also my neighbors' neighbors and their neighbors. If you want to see the difference, have a look at my previous video tutorial. Click on that, 0.7. So you can see it's much more bunched, it's much more varied, it's got the lag. 0.7, it's still high, but it's not as statistically significant as Moran I. The first order, go randomization, let's go 99 again. We open it, it's still statistically significant. So it's still statistically significant, however, the strength of the relationship have weakened. So including more neighbors is actually diluting the relationship compared to having less neighbors. So in this case, less neighbors are more better than more neighbors. So let's quickly have a look at same and have a look at the rook is the same. Let's go k nearest. So here we forced it to 4. I think if I can vaguely remember when queen order 1, I think it was between 7 and 8 was the most neighbors. Here we're forcing it only to 4 neighbors. So let's see what that looks like. Press OK. You can see 8, 6. So similar to the queen 1. And if we do randomization, let's go there. 0.01. So between the k nearest 4 and the queen order 1 weight matrices, there doesn't seem to be any significant difference. Let's have a look again at ndvi. Let's use uniform and we press OK. 0.75, because again, if you compare the uniform and the order 2 number of neighbors were actually quite similar. There wasn't too much of a difference between them. So yeah, so have a look at the weight matrices and see the impacts. As I said, this is actually where you see where the differences lie. So just from this bit, it does show that having fewer neighbors or closer neighbors yields higher Moran I values or spatial correlation than more. So when we do regression, we'll actually use fewer neighbors in our analysis than more neighbors. So in this case, the further you are from a particular location, the weaker your impact, which makes sense to some degree. Okay, so let's quickly look at the bivariate, and we said we're going to keep it ndvi, and we're going to keep and make it rain, and we're going to do queen 1. So let's do that, and that is indicating at best some sort of positive relationship between lagged rain and ndvi. If we do the randomization, let's quickly go up to 1000. Let's run it. It's still statistically significant. Let's do 99. Also still statistically significant. So this is also statistically significant, this value. However, it's basically indicating there's virtually no relationship between ndvi and lagged rain. Now that is using, let's quickly go back there. That is now obviously using order 1. So let's quickly go order 2 to see whether now it's worthwhile including more neighbors. It's exactly the same, plus minus the same, plus minus the same. Let's have a look and see what that value, where's that value? That value is there. So that means there's no relationship. And that most probably is bare soilish area. So whether it rain or not is really irrelevant given that it's most probably bare soil. So I would think that that is bare soil. Okay, so that is then, and we can do it now with, let's say with elevation. Elevation is on top here. Elevation, let's keep it with queen 1, see what that works. So that's sort of, we are thereabout. You see it's very clustered. But anyway, this is, you can play around with that. Differential Moran I statistics, test whether change is spatially correlative. Okay, so let's leave that out. That doesn't want to seem to want to do it. Moran I with EBE rate. Let's do the same and see what that does. Oh, that's high. So that is now lagged ndvi divided by elevation. So that is ndvi divided by elevation, divide by ndvi divide by elevation, current location, divide by lagged ndvi, divide by lagged elevation. So that gives you quite a high Moran I statistics. That's very, very close on this correlation coefficient. So that's, what was that one? That was EB rate. So that is a ratio rate. Okay. So it's a ratio of Moran I, ndvi and elevation current versus ndvi elevation lagged. So it tests that relationship. So that is testing the Moran I statistics and variations there. Now we're going to go to the univariate local Moran I statistic. So in this case, we include the region of interest as a whole. So let's click on that. Let's quick do the same. And let's just do the Moran I first. Because now it's possible to do clustering and significance, which we couldn't do with the previous one, because in this one, we include our region of interest as a whole, or not just the specific locations. So if we do this one, the Moran I statistic, you'll see it's exactly the same, 0.82. Let's do the same here, just to confirm, 0.82. So in terms of the Moran I statistic between the univariate and the univariate local Moran I, there's no difference. Okay, so in terms of the Moran I statistics between these two, there's no difference. However, when we do the local ones, you'll see we have the option of doing a cluster map and a significance map, because now it looks at the whole region of interest and not just at the locations as individual parts of my region of interest. It actually combines the whole thing now. So let's do all three of them. As I said already, the Moran I statistic will be the same as the normal univariate one. We click OK, and it will generate 3. This one we've already seen. Okay, so let's keep it, because what's interesting now, or what's useful now, is you'll see all these maps are interactive. So if I click on one of these ones, let's click on this one. It will show you on the map, on the region of interest map, where it is. It will show you in the significance map where it is, and also in the clustering map where it is. The LISA cluster map and the LISA significant map, and here's my normal Moran I statistic. So I select it there, and it said it will show on all 4, and that again is part of the beauty of GeoDA. It's very, very interactive from a spatial point of view. Okay, so let's quickly just unselect. Now what it means is there's 4 quadrants, or 4 options here. 5, sorry, not significant. Okay, so high, that's the 4. I want to do high, low, high, and high-low. So that's the options that you have here. It's high, meaning these locations have all high values together. Low, all these locations have low values together. And low-high is they have, because remember there's 2 axes. That's a lagged ndvi and the ndvi. And the one they have a low value, and the other one they have a high value. So it's basically these 4 quadrants that you put here. So let's put this one here. So that would be high. Okay, so let's click here. Sorry, man. Come on, why don't you? I don't want to do this now. You see there? High. There it sits. Okay, so that's high. And then low would be here. If we select that one there, should be in the blue area. See there, the blue. And if you have here, let's select this one there. That's going to be either low, high, or high, low. Which one will it be? Let's select it. Hey, you have to be so precise. Where it is? Oh, it's sitting there. And let's have a look and see which color is that. Now, it's a bit difficult to see with that color. Yeah, that's low, high. So that would be low and high. And this one is high and low. So let's select that one there. Okay, you have to be so careful. Be on the dot with it. And it's located where there. That's where it sits there. It's on this one there. So that's high, low. It's one of these ones. So this four groups, high, high, low, 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 high, high, low, corresponds to this four quadrants here. So that one there is high, high. So you see a lot of values on high, high. 9, 6, 8 of them to be precise. So if you count it, it's high, high there. Low, low, it's these values there. And there is 1,138 of them. You can see them all scattered here. So they have both low values of that and low values of lagged ndvi. Then low, high, that would be this one, that quadrant here, low ndvi, high lagged ndvi. And then the opposite, this quadrant here, is high ndvi and low lagged ndvi. And I said these locations are all plotted here. Now this is whether you see there's the 990 permutations, that's generating the significance of each. And you see in general the high, high and the low, low are statistically significant at the 0.001%. These low, high, high, low, 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 high, low, high, high, low in general are not statistically significant. So the statistically significance of the correlation statistics, or correlation, the Moran I statistics is based predominantly on the high, high and a low, low cluster, meaning around this particular function, spatial correlations function, this one here. Okay. So I hope that makes, you'll see the total is 4,903 observations, 4,903 observations. So that is the LISA significance map and the LISA cluster map. Now this is, as I said, I found particularly useful when I do my consulting work and my analysis work. I include a lot of this work because I think this is quite useful, especially when you do spatial related work, is this clustering of values. Okay, so that is then the univariate local, univariate median local statistic. Let's look at it that way. Cluster map and significant map. It's what we've presented just now. Nothing to that. Bivariate local Moran. That's now when you select ndvi. Let's keep it elevation. Queen R. Let's do all three of them again. Although we know the scatter plot, what was going to be that one was also very low. That one was also very low, yeah, 0.48. Have a look where they sit. You can see now the low, low, high, high, and low, high, high, low. You can see the low, low, and the high, low are quite mixed. The high clusters are again clustered. There is, yeah, that's the low, low. That's a sandy area, that's a natural area. So that's low elevation and low ndvi. And you can see the significance map as well. And again, I think the same interpretation. That is high, high, low, 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 high, high, low. Okay, so I think that is fairly self-explanatory. Differential, local, that's the same. Now let's go to the local G. So to a large degree, these statistics, these two categories of statistics are the same, except that the second category allows you clustering and significance because it is focused on the region of interest. Now let's look at the local G. Let's look in. Now I've kept my weights as Queen 1, okay? So that's another variable that you need to take into account when you do this. So let's go Queen weights. Let's go use row standardized cluster, okay? It looks similar to the low, low, high, high, statistically significant. It's a G, it's nothing much to it. It's the same as our univariate local Moran. Not going to go there. What I wanted to do is spatial correlogram. Okay, so the variable here, let's have a look at ndvi and ndvi, and that's our spatial correlogram. This is also fairly useful. It gives you an idea of the the distance of spatial influence. Gives you the distance of spatial influence. So you see, at close distance, there's fairly high spatial influence. And as distance increases, the spatial difference becomes 0, and then it fluctuates around this 0. So this gives you an idea of the distance of spatial. Let's go to arc kilometer. Arc kilometer, that's 10 kilometers, 20, 30. So basically by 10 kilometers. So at that value there, which is about distance, okay, they don't tell you exactly the distance, but we can estimate sort of 5 kilometers. There's high degree of autocorrelation or spatial Moran. And then by 10 kilometers, that spatial influence is basically 0, and then it fluctuates around the 0. So it gives you an idea of the distance of the spatial correlation. And we've seen it that the order 1 queen, which is neighbors, direct neighbors only, is much higher than the second queen, where we look at their neighbors as well. Number of bins, maximum distance. You can play around with this. But that's quite a useful tool, as I said, is to measure the distance of spatial relevance or spatial influence. But you can see the spatial influence is quite limited, 4 or 5 kilometers, and that's basically that. So that's quite useful. So that is working on spatial correlogram. Distance scatter plot. Let's have a look at C again. That one there. Let's go equivalent distance. Let's go apply and see what that looks like. All pairs, random sample. Okay, there's a lot of them, so it's taking a bit of time here. So there we go. Apply, and then let's go cancel. Variable distance, so that's again, come on. That's again showing the distance, geographical distance, and the variable distance. You can do the interpretation. That's where, let's have a look and see, where the local univariate, local G, I'm not going to go for that, correlogram, it's not showing that specific one. What's it called, a name again? It's distance scatter plot. Let's quickly just delete that one now. So let's go back, and it's not saying the distance scatter plot, can't say it, but it's got the correlogram, which is basically this one that we did here, spatial correlogram, okay, which calculates the distance of influence. So let's click on that one there. It will take you to a site, and it will tell you that what it's all about. Creating a spatial, gives you there the number, the bins. There's very similar to this interpretation. Okay, so there's the interpretation of it, etc. So it's quite a useful. Let's see if it includes. No, smooth distance scatter plot. No, it doesn't include those ones. Yeah, there we go. It includes this one as well. So you can read distance scatter plot. Yeah, so it's under the same heading. It indicates with the just plot using bring all over pattern more clear, but general plot increase until a distance of about midway feet, after which it flattens out. So it's the same sort of interpretation, just in inverse. Okay, so that's where this GeoDA cheat sheet becomes quite useful, is to work on those sort of things. So that is working on this spatial correlation or spatial Moran statistic and all the options there. It's maybe a little bit repetitive. Univariate local GeoDA, that's also, I think, quite nice. Cluster map. to a main, to a lot. Oh, this is quite. This is high, high. Well, just different colors. High, high, low, low. Other positive, negative. So it's just the same. Just present a little bit way. But the ones that I tend to use the most is this univariate local Moran. So that's fairly, and then the bivariate one as well, and then the spatial correlogram. So that's the three functions that I tend to use 90% of the time. But as I said, make sure that you play around with the spatial weight matrices, because that does make a huge influence. So you might be statistically significant with order 1, and order 2 comes, everything falls flat. So just make sure of that. But that's, as I said, where I think the real power of GeoDA lies, is to generate the spatial the spatial relationship maps. And I think that's for which I think is very useful. So that to me is the real strength of GeoDA. It's able to generate these things. I don't know whether you can do this in R or QGIS or Earth Engine. Definitely not in Excel. I don't think you can do it in QGIS. I've never seen this done in R. And I don't think you can do this in Earth Engine. So, as I said, that's where the niche of GeoDA lies, in my personal view. This is the beauty of GeoDA. Okay, so yeah, thank you very much. It was great having you on board for this particular video tutorial. Thanks for your support. Thanks for subscribing. Thanks for liking and sharing. I appreciate your comments. We'll get to all the suggestions in due course. I've seen them all, so we'll work through them. Got some interesting ideas on some things that we have to do. So keep it coming. We'll get to all of them. So with that said, thank you very much again. Appreciate it. Thanks for joining me on this journey of remote sensing, and I'll see you on the other side.